Okay. Hi, everyone, and welcome to our session, the last session of the day, which is about model interpretability. We're going to be taking a look at first introductions about model interpretation and explanation. And of course, we're going to have a demo just to have a better understanding with it. So, as usual, just raise your hands or just open your mic and speak if you have any questions, okay? Yeah, let me share my screen. Actually, let me share the whole window. Can you see my screen, guys? Is it visible? Okay, thank you for the confirmation. So, okay, let's talk about model interpret. Sorry, like for the word, it's a tongue twister for me, I guess. So let's take a look at it. Okay. So let's start talking. Let's start with talking about the problem, which is the black box problem. You can call it. So we're gonna have two scenarios. The first one is the black box and the white box. So I will explain what each means. So the black box represents like we have these powerful and very accurate machine learning models, such as DNA or deep neural network or gradient boosting machines and so on, which are effectively black boxes. So of course we have the decision tree, which we can consider the white box, and of course logistic recognition. Also, we can call it a white box. So, but what do we mean by black box? White box. So black box represents we can see the input and we can see the output, but we cannot see the internal logic that is so complex that it cannot be or it's not human understandable. So for the white boxes, of course, for the like that for the tree, you can take a look at the decision tree, and you can see why a certain decision is made, or why a certain output is seen. And the same for the logical regression. Of course, we will see it what we mean, but for DNA and gradient boosting machine modules, we cannot see, or it's not human understandable. You cannot easily understand why a certain decision is made or a certain output is displayed. For instance, let's take an example. So you have, let's assume you're working at a bank, and you can see that. So you have a client that came in and wants to, get a loan from your bank. So the first thing you're going to do is ask the applicant to fill out the forms, right? So you gather their information. It could be about income level, age, the credit score, debt to income ratio, and so on and so on. So you're going to take in a lot of inputs to make your decision, right, for the model. So the model, which is a highly accurate model, but complex neural network model that you have trained for this specific purpose. And the output shows that you should deny 90% the loan, okay? So you have rejected the loan, but you or the applicant do not know why the application is rejected, right? So is it because the person has a low income? Is it because the person has a short credit history? Or does the person have a high debit? Is that the reason? Like, of course, like if the person has these reasons, it could reduce their chances of getting a loan, but why they did it, reject the loan? So could it have been an error in the input data? So this is very crucial, because if the error is from your side, you're going to lose a customer, right? Or from the data, you're going to lose the customer. And what can the applicant do in order to improve or to get approved in the future? So you need to answer all of these questions and but you can't, since the model is very complex neural network model. So model interpretability is going to help you with this one. Okay? So we have no answers without it. So this leads us to loss of trust. So since it's not clear, since it's black box or it's all hidden, or like the reasons and like everything is hidden, the customer could lose trust in you. Potential regulatory non-compliance, especially in the EU. Like there is a law, I think, I don't know if it has been passed, but I believe there is a law that uh, basically forces you to explain why you have rejected the person and so on and so on. And poor customer experience. Since the customer doesn't know why he was rejected, he could he is not going to be happy with it. The customer experience is going to be bad. So so explaining the model or why the model output gave you a certain output is very important in order to answer all of these questions. Okay? So it's a very interesting thing and should be part of your pipeline every time you work with a model, because it helps you identify bugs if there are any in the model, identify which features are more important, and so on and so on. So we will see all of this. But before that, let's talk about interpretability and explainability. So of course, sometimes we may use them interchangeably uh, with one another, but there is a very useful distinction between these two. So interpretation or interpretability is the degree to which human can understand the cause of a decision by looking at the model itself. So they do not need to go anywhere else, but they can see the model and understand why a certain decision has been made. So the nature, so this is an intrinsic property of the model. The model is simple and transparent, such as it could be a linear regression model, or it could be a decision tree model, and so on. So its interpretability is caused by examining its coefficient. So we will see if this term is new to you guys. Don't worry about it. We will see what coefficient examining the coefficient means to so you can do that to understand its logic. So you will know why a certain decision has been made just looking at the model itself. And for explainability or for explaining, so it's the degree to which the internal mechanics of the machine learning model can be explained in human terms, often using a separate technique. So the model itself could not be or may not be enough for explainability. So we can use like a separate technique such as line or sharp and so on. So the nature is this is a post hoc or after the fact analysis. So we can apply these external tools trained to a trained model of the black box, which is like a neural network and so on, to generate explanations. So, for example, you can use SHAP to generate a report explaining why a complex neural network made a specific prediction. So this is very interesting. So taking a look at inside the brain of the machine. So you can think of it as taking a look at inside brain or the brain of the model, seeing how the features affected its decision making and so on and so on. In short, an explainability model is its own explanation. Sorry, interpretable model, its own explanation. So if the model is interpretable, it has like you can consider itself to be explanation. An explanation model requires a separate explainer to translate its logic. So I hope this is clear. So before I move on, is it clear? Does it make sense, guys? What I've just said. Okay. Good. Okay. Yes, Mikael.
Okay, can you hear me?
Yes.
Okay, somehow I can kind of grasp what you are talking about. But what I don't understand is, since, like you say, the code is a kind of a black box. If it is a normal software logic, we know that the logic, based on that logic, we can give some kind of explanation why something is happening. But in this case, uh, the model by itself, it was uh, learned from the data and make some decisions. So what we are trying to do is here, whenever some kind of decision made by that model, we are going to make some kind of explanation, right?
Um, it's half right, I would say. I would say it's half right. So the
Okay.
post hook, of course, for the post hook, you are correct. So after the decision is made, you can take a look at the individual decision and try to see why that decision has been made. But for the white box, of course, for the black box, you are correct. But for the white box models, so for the white box, it's interpretability. So which means the explanation is itself. So the model itself can explain or could show you uh, the logic which you have which you have mentioned earlier. So you already have the logic if the model is a white box model because it's simple. You can see the decision tree coming down and the output, why the output happened, and so on and so on. But for black boxes, that's not possible. Of course, there are four methods that we're going to see. The two are local, and the rest two are going to be global. But uh, we will get to that. But to answer your question, like if the model is black box, yes, you are correct. Like you can take a look at the prediction and try to see why that prediction has been made. But it's for if it is for a white box model, you don't have to go there. You just have to you can see like the coefficient of each the coefficient of each feature, or you can see the tree of the decision tree that the model is going to follow. And you can, even if you have the data at hand, you can guess what's going to happen just by looking at the model explain interpretability.
That means if we know those features and the model is going to give us some kind of weight. Is that what you mean?
So let's classify white box and black box. For the white box, for the leader recognition, yes, it's going to give you weight. So are you talking about the black box or the white box models?
I'm talking about the black box because each model will have multiple features.
Mm.
So the decision is based on those features and
Mm.
additionally the weight of each features, right? So whenever some kind of decision made by black box model, we are going to.
It's not that easy though. Like it's not like I understand the question now, but it's
Okay.
not as easy as having a coefficient when it comes to complex models such as the neural network.
Kerad, may I say something
Uh,
in regards to
yeah,
this?
yeah, sure.
So, if, for example, if you look at how neural networks work, you essentially have your one layer, then you have an activation layer, then you have many different hidden layers. And for every single hidden layer you go through, you remix the features. So you're right. In the end of the day, once you're done doing through your neural network, what you will end up with is a list of features with a list of feature weights. However, those feature weights are so far removed from the initial features through all the different hidden layers and through all the activation functions, it is nearly impossible to see how the end list of features actually were derived from the initial list of features. And that's just if you're looking at a purely mathematical one. Now, if you're looking at categorical variables, or even worse, an LLM, what happens is you're actually going through a vector space and you're looking at vector distances through the LLM vector map. And then it gets even harder because now you have to do embedding and you have to do vector mapping as well, adding in other layers. So the human mind, there's no way to actually keep up with it. So one of the only ways to really explain something like a neural network is something that's post hoc. Now there are a few other methods, but the primary method is like post hoc. Now for something like, let's say, gradient boosting, you have a bit of options. You can look at gradient boostings and you can simply look at the results and do post hoc, or you can go with a white box model like an EBM, which will actually take the individual trees from each feature and add them up together later additively. So that could be considered a white box, which is natively explainable. But you have to understand that for some models, it's simply impossible to have a white box version or to just look at the feature weights. It won't really help you because they're recombined so many times that they're really meaningless in terms of interpretability by the end of the day. That's it from my side.
Thank you, Neville. That's what you are explaining is it's a technical part. What I want to understand is that's the interpretability and explainability concept is the way we are kind of giving our reason to our customer, like the example of this slide. This decision came because of these features or because of something other thing. So those decisions, the reason of those decisions will be given by something.
Of course. Oh, I think I understand
want
the
to-
question now. So for this example, like for interpretability and explainability, if you are focusing on this specific slide, yes, for at the end of it, we're gonna use the output of like for the white box or for the black box, we're gonna use interpretability or explainability in order to explain like which features or what caused what in order to come up with the output. So if that's the question, yes. At the end of it, we're gonna use them in order to explain why something happened.
Thanks.
Yeah. So
I will come up with a follow-up question when the slide is.
okay, good. Thank you for the question, Andrika and Nabil. Yeah, okay, I think let's move on just to save time. So why is it important? Like, why is this important? So for most of the time, it's for academic exercise, but it's not only limited to the academic exercise, but it's very critical or important for the real world application. So like here are some list of things that that could be some motivations in order to help you or to help you understand why we are doing this. So for the first one, and I would say the first two are very important. The first one is debugging and auditing. So the model makes strange predictions. If a model makes strange predictions, like by using interpretability in your primary debugging as your primary debugging tool, it will help you uncover or discover if the model is relying on correlation. For example, a background artifact in an image, or reacting to a debug in the data pipeline, or if the issue with the data input itself. So the first one is debugging and auditing in order to help you debug why some strange prediction is happening. Is it from the model? Is it from the pipeline? Is it from the input? Or is it from something else? And the next one, which is also very, very important, would be fairness and bias detection. So it's very important because interpretability can reveal whether a model is unfairly discriminating against protected groups. For instance, Is a model using features like zip code or country in order as a proxy for race? It's very dangerous if it is doing that in order to account for it or in order to change some things. Or is it unfairly penalizing women applicants and so on? So you need to check for these kinds of bias. Regulatory compliance. So as I think tried to explain earlier, like there is some rules or frameworks, legal frameworks in Europe for algorithmic transparency. For instance, it includes a right for or to explanation, which means companies may be legally required to explain the decision made by their automated systems. And of course, building trust and that adoption. So for the beginning, at the beginning of the slides, we have seen an example of loan. So for these cases, in order to have trust and to help others adapt to AI system and trust it, in order to have confidence in the decision-making process. So showing them why something happened is going to make them trust the system. And of course, the last one is scientific discovery. So sometimes the goal is often to not just predict, but to understand why something is happening. So a model trained on data, on I think, genomic data, for example, can help biologists discover a relationship between genes and diseases. So it's very important to explain, to know why something happened, why to know the decision made, the reason behind the decisions made, and so on. So taxonomy of interpretability models. So we're gonna look at two primary axes, which is going to help you choose the right tool for the job. So we're gonna see intrinsic versus post hoc, and we're gonna see global versus local. So for the intrinsic versus post hoc, is the explanation built into the model? So is it a black box or a white box, or is it generated by separate tool after the model is trained? So this is basically post like a white box or versus black box. And the local versus global is that the explanation describe the model's entire behavior. Are you talking about the model, or is it explaining a single prediction? So if you are explaining a single prediction, it's local. And if you are trying to see the model's behavior as the whole, you're talking global. So I think you can also see this simple table in order to help you understand it more. So if it is global and if it is intrinsic means white box models. So you can understand all the coefficient in a linear model. You can see overall feature importance from a simple decision tree. But if it is for local, you can follow a specific if-else path for one prediction in a decision tree. So we will see what we mean by this one. If it is post hoc and you're talking about global, you can have two options, which is PDP, which is how does the feature affect predictions on average, or permutation feature importance, which feature are more important on average. And for local, which is after you have like for post hoc, but for local, after you see the output, you want to see why the output, like the features, how the features play their role in the output. For Lime, it can create a local simple model to explain one prediction. And for Sharp, it's a game theory. It's going to assign contribution value to each feature for one prediction. So you can consider it as a game. You have the game, you have the players, and you have the payout. Sorry. So for each feature, you can consider them as the players, and the weight you can consider it as a payout. And for the game, like for the participation in the game, you can pay out the features by like their importance or by how important they are. So let's take a look at the white box models first, and then we will move to the black box explainability methods. Sorry. So for intrinsic interpretability or the white box models, it's just a straightforward interpretability. is to use a model is transparent, that is transparent by design. So for this example, we have two very simple models, which is the linear regression and the decision tree. So I think you, most of you at least know the house price prediction data set. That's you can pretty much find it everywhere, but you can also find it on Kaggle. It's a model, like the model captured in a simple human readable equation. So the model can be explained in an equation. So we have beta 0, beta 1 multiplied by the area, which is square feet. Subtract beta 2 multiplied by age and epsilon. So for this explanation, you can see that the learned coefficient beta is directly tells us about the relationship. So for example, if beta 1 is $205, you can like 250, you can see that 250 for every additional square foot of area for that house, the price is going to go up by 250. So you can directly see it by just looking at the formula. Of course, we can see also the coefficient, the coefficient weight by taking a look at the demo. Okay. And for the decision model, you can just have a flow chart of if-else questions. If this happens, then this happens, or if that happens, that's going to happen, and so on. You can visually trace the logic in any decision. So for example, if credit score is less than 600, then if debit to income ratio is less than or greater than 0.5, then deny loan. So this is very like, you can follow the tree in order to arrive at a decision. So it's very clear, an ambiguous explanation for why a specific loan was denied. So of course, there is a trade-off. While it's very highly interpretable, these simple models cannot capture complex pattern in the data and often have lower predictive accuracy than black box models. Okay, so we have seen that. So let's take a look at the local explanations by postcode, which are LIME and CHAP. So for the LIME, it's short for local interpretability model agonistic explanation. So it's just going to help. It's going to explain the individual predictions of any model, no matter how complex it might be. So the core idea is very interesting, actually. So it's hard to understand complex model globally, but it's very easy or easier to approximate it locally. So this tool, LIME, is going to generate a new temporal data set around a single prediction, and then trains a simple interpretable model like a linear regression on that small data set, and is going to use that the explanation from this model to serve as explanation for the higher or the complex model single prediction. So it's very actually interesting. For example, the husky versus wolf example is very so the model is trained to classify image of husky and wolves. So it correctly identifies the image as wolf. Okay, so that's good. So for the black box prediction, you can see that it's going to say wolf, and when you take a look at the image, you see that it's correct. But for when you take a look at the explanation, you can take a look at LIME and how it highlights the pixel that help the model to identify the picture as a wolf or the animal in the picture as a wolf. So for example, if it reveals that the most important pixel were not the animal feature, but the snow in the background, that's not going to be good, because the model did not learn in order to identify wolves, but it has learned to identify snow. So if there is a snow, wolf lives in a snow, and it's going to say it's a wolf. So LIME helps you catch these kinds of dangerous correlations. So if there is a snow, there is a wolf, and if there is not snow, it's going to be husky. So that's the output from this example. So by using LIME, you can identify these kinds of issues early on. And of course, for the gameplay, the game theory analogy, you can see CHAP, which is actually short for sharply addictive explanations. So it explains individual prediction by quantifying its features contribution grounded in comparative game theory and Shapley. So the core idea, we have the game, which is the prediction, the players, which is the feature, and the payout, which is the model as a final prediction. So you can take a look at this as so shape values are a result of fairly distributing the payouts among the players, presenting each features contribution to the final prediction. So you can see that, for example, okay, I think it's better to talk about this with the example, but we have the base value, we have the red arrows, which are the features that pushing the prediction higher than the average, and the blue ones are the features that are pushing the prediction to the lower than the average. And the size also shows the magnitude of the arrow, sorry, the magnitude of the effect. And the final prediction is just the sum of the base value of this feature prediction. So some features will have a blue arrow and some features are going to have a red arrow. So the sum of these things is going to be the features, sorry, the final prediction. So what we have looked at for the two examples are global, local explanations or explainabilities. And now let's take a look at the two global explanations. So we have the first one is permutation feature importance. So this is very interesting actually. So the goal is to move from a single prediction understanding the model as a whole. From a single prediction to understanding the model as a whole. So from the previous two, we were seeing that understanding the model from the predictions, right? No, understanding the single predictions, but for the global is understanding the whole models. So which features are most important on average across the prediction? That's what we are trying to answer with permutation feature importance. So if a feature is important, then breaking its relationship with the outcome should significantly damage the model's performance. So for instance, So train your model and calculate its performance score on a test. So let's say first you have a 92% accuracy, and then you're gonna shuffle the features, take a single feature, for example, age, and randomly shuffle its value, and then reevaluate it and see the accuracy. So you can see that the accuracy has dropped to 75%. So the importance is 17% because it has dropped the accuracy from 92% to 75%. So, and repeat this for every feature in order to see which feature is very important. And the last one, which is for the global explanation, we have the partial dependency plot, or PDP. So this visualizes the marginal effect of one or two features on the predicted output of the model. So it helps you to understand or answer how does the model's prediction change on average as I vary these features value. So for example, so you create a PDP for a single feature, let's say age. So you have chosen the age of 30. So you want to see how this change is going to affect the model as a whole or the features value. So you go through the data set and force every single data point to be 30 for the age, and do the prediction again for these modified data sets. And the point on the PDP for age 30 is the average of all these new predictions, and repeat this process for different age values, 31, 32, and draw the plot. So it's a very pretty, I think, it might be a little bit harder than the rest, I believe. So it can show you the average prediction price change as the square footage increase. But here you have to be very careful. Actually, you can show you the average predicted price as a square. So age should be age, but yeah. I'll change that, but this assumes that the feature you are plotting is not correlated with other features. But for example, if age and income are correlated, it's going to be very misleading because you're going to be assigning the 40-year-old's income to 20-year-old. So that's not going to be realistic. So you have to use it with care. Yeah. So finally, let's take a look at some key takeaways. Are black boxes introduce risk because you are relying on models you don't understand how they operate. It's not best practice to do so. So it can lead to costly errors, like perpetuate harmful bias, break customer trust, and violate regulations. So by using interpretability which is a spectrum, you can face a choice: either build an intrinsic simple model or a white model from the start, or build a high performance complex model and use a post-hoc technique in order to explain it. So lastly, like think both locally and globally to complete understanding of these two will give you both perspectives. So use Lime and SHA for local and PDP and permutation importance for the global. So Lime and SHA will help you debug individual predictions and build user trust, and the permutation importance and PDP help you understand the overall model and strategy and what is the most important drivers for the model or for the decision making. And lastly, make the interpretability part of your workflow. So this means do not treat this as an optional add-on to the end of your project, but it should be core component of especially machine learning life cycle. So from the initial data exploration, feature engineering, throughout the model debugging and validation to deployment, it's good to have this interpretability integrated into your system. So that's it from my side. I think I took a lot of time, but I hope it was worth it, because it's very important for you guys to understand this part. So is it clear, guys? I want to see if there are any quick questions. Let's ask. Yes, Sound Mikael.
ጥያቄ በአማርኛ ላድርገው የበለጠ ግልጽ እንዲሆንልኝ ማለት ነው። ችግር ከሌለው
It's okay. You can go.
ማለት አሁን ልንጠቀማቸው የምናስባቸው እንትኖች እነዚህ ላይብራሪዎች ላይምም ይሁን ሻፕ ሞዴል አግኖስቲክ እንደሆኑ ነግረህናል። የሆነ ፓርት ላይ ላይም ሎካሊ የሎካል ሜቶዶች ነው። ሻፕ ደግሞ ኦቨርኦል ግሎባል
ነው። ሻፕም ላይምም የሎካል።
ኦኬ። ስለዚህ ማለት ዘው አንደርስታንድ አሁን የምናደርገው የሆነ ሞዴል some kind of decision ፕሪዲክት አደረገልን ብለን እናስብና ሎካል ስንል ዋን ፊቸር ነው ወይስ ከአንድ በላይ ሆኑ
ፕሪዲክሽን? ዋን ፕሪዲክሽን ሎካል ስንል አንድ ፕሪዲክሽን ነው የምንወስደው። ለምሳሌ ስለ ሎን የምናወራ ከሆነ ይሄን ሰውዬ ዲናይ ያድርገዋል አይደለ? ሶ I'm going to focus on ያቺን ፕሪዲክሽን። ከዛ በኋላ ያቺ ፕሪዲክሽን ዲናይ ለማለት ሞዴሉ ምንድነው ያየው የሚለውን ነው። ፊቸሮቹን የትኛው ፊቸር ለዲናይ አመዘነ፣ የትኛው ፊቸር ለአክሴፕት አመዘነ፣ ከዛ በኋላ ደግሞ እንዴት ዲናይ በለጠ የሚለው ነው ለሎካል ሲሆን።
ስለዚህ ለእንትን ሲሆን ደግሞ
ለግሎባል ሲሆን ደግሞ ሞዴሉ የሆነ ፊቸር ሲቀያየር እንዴት ነው ትሪት የሚያደርገው? ለምሳሌ ኤጁን ሲቀያየር እንዴት ነው ፕራይሱን አፕዴት የሚያደርገው? ኦር ደግሞ ለምሳሌ ኤጁን ሲቀያየረው የሞዴሉ ፐርፎርማንስ እንዴት ይወርዳል? ምክንያቱም ምን ያህል ነው ኤጅ ላይ ዲፔንድ ያደርገው ይሄ ሞዴል። ገባኝ? ሶ ፊቸር ኢምፖርታንስ ነው ኦፍ ኮርስ፣ ግን እንዴት ላይክ አፌክቱን ላይክ ኦን ዲ ኦቨርኦል ፐርፎርማንስ ኦር አኩሬሲ ኦፍ ደ ሞዴል ፊቸሮቹ እንዴት ነው አፌክት የሚያደርጉት የሚለው ነው ማለት ነው። ሶ አንዱ ሎካል ስንል ያቺ አንዷን ፕሪዲክሽን ለመምጣት የሄደበትን መንገድ ነው ኦር ደግሞ ላይክ አፌክት ያደረጉትን ፊቸሮች እንዴት ነው አፌክት ያደረጉት፣ ፖዚቲቭ ነው ኔጌቲቭ ነው፣ ከዛ በኋላ ደግሞ ላይክ እሱን እናየዋል። በዚህኛው ደግሞ በግሎባል ስንል ደግሞ we are not talking about a single prediction but the model itself ሞዴሉን ለማየት ነው እየሞከርን ያለ ነው ማለት ነው።
Thank you, guys. ስለዚህ let me the second question. Model agnostic, it should work only. It's a general kind of mechanism to explain what is happened. There are also additional model-specific libraries, right? Such as attention mechanism, tree vector. So, እንዴት አሁን እነዚህ ሞዴል አግኖስቲክ እና ሞዴል ስፔሲፊክ የምንላቸው አሉ። ሞዴል አግኖስቲኮቹን ለኤኒ ካይንድ ኦፍ ሞዴል መጠቀም እንችላለን የሚል ሴንስ ነው አይደል ያለው በዚህ ኬዝ እና
ቀጥል።
ስለዚህ እነዚህ ለምሳሌ ሞዴል አግኖስቲክ ከዚህ ውስጥ ላይም ሻርፕም አሉ ለዲፕ ለርኒንግ ልንጠቀማቸው እንችላለን።
ሞዴል አግኖስቲክ እኮ ስሙ ነው የላይም ስሙ ነው ራሱ ሞዴል አግኖስቲክ። ላይምም ሻርፕም ሳይሆን ላይም ሲተነተን ሎካል ኢንተርፕሬቴብል ሞዴል አግኖስቲክ ኤክስፕላኔሽን ነው ስሙ ነው።
ያኛው ሼፕሊ አግኖስቲክ ሞዴል ሳምቲንግ አይነት ነገር ነው የሚለው።
ይሄኛው ደግሞ ሻርፕሊ አዲቲቭ ኤክስፕላኔሽንስ ነው የሚለው።
ስለዚህ አሁን ለዲፕ ለርኒንግ መጠቀም እንችላለን እነዚህንም።
ኦፍ ኮርስ እሱ ነው የምንጠቀማቸው እኮ ለዲፕ ለርኒንግ እና ለእንትን ነው የምንጠቀማቸው እነዚህ ለብላክ ቦክስ የምንላቸው። ለዋይት ቦክስማ ራሳቸው አላቸው። አሁን ለዲሲዥን ትሪ ራሱ አለው። አያስፈልገንም ኤክስትራ መጠቀም ራሱ። ኦፍ ኮርስ መጠቀም እንችላለን አንችልም እያልኩ አይደለም፣ ግን ራሱ አለው። ምክንያቱም ላይክ አሁን ለምሳሌ ዲሲዥን ትሪውን ሳለ ስትለው ትሪውን ቆይ ለምን ኤግዛምፕሎች አናይም? አይ ቲንክ ኢትስ ጉድ ቱ ሲ ዘ ኤግዛምፕል። ሶ ላይክ አሁን ለምሳሌ የኮሪሌሽን ዌይት ነው አይደል? አሁን ይሄኛው ለምንድን ነው የምንጠቀመው? ለሎጂስቲክ ሪግሬሽን። ሶ ዊ ሲ ዋይ ላይክ ለምሳሌ የሆነ ነገር አሁን ይሄኛው ለብሬስት ካንሰር የሚባለው ዳታ ሴት አይ ቲንክ ላይክ ኢትስ ቬሪ ቤዚክ እና ብዙ ሰው ያውቀዋል ብዬ አስባለሁ ይሄኛውን ዴታ ሴት። ሶ ዘ ዋይት ሞዴል ስለሆኑ እነዚህኞቹን ኮኤፊሽንት ላይክ የፊቸራቸውን ኮኤፊሽንት በማውጣት ዊ ካን ሲ አንድ ነገር አሁን ለምሳሌ ወደ ፖዚቲቭ ሰውን ቤኒንግ የሚባል ቤኒንጅ ነው አይ ቲንክ አይ ዶንት ኖ ቴክኒካል ተርም። ወደ እሱን ለማምራት በጣም አፌክት የሚያደርገው ማን ነው ማለት ነው? የቴክስቸር ኢረር ነው። የቴክስቸር ኢረር is going to affect it ወይ ደግሞ like more texture error ካለው ወደ more ወደዛኛው ያምራል የሚለው ያሳያል። እዚህ ጋር ደግሞ worst concavity ደግሞ ካለው ወደዚህኛው ያምራል ማለት ነው። ሶ እነዚህኞቹ ኮኤፊሽንት ኢረር ናቸው። እዚህ ጋር ደግሞ ዲሲዥን ትሪዎችን በምናይ ጊዜ አሁን እዚህ ጋር like ይሄ ነገር አለው ወርስ ሬዲየሱ ከዚህ ያነሰ ነው ወይ ጌኒው እንደዚህ ነው ወይ ሳምፕሉ እንደዚህ ነው ቫልዩ እንደዚህ ነው ወይ ከሆነ ትሩ ከሆነ ክላሱ ቤኒንግ ነው፣ ኖ ከሆነ ደግሞ ማሊንጃንት ነው። ሶ እንደዚህ ያለ ዲሲዥን ትሪውን መከተል ይችላል። ሶ እነዚህኞቹ እንትንም አያስፈልጋቸው ይሄ ላይምም ሻርፕም ፒዲፒም ምንም አያስፈልጋቸው። ኦፍ ኮርስ መጠቀም ይችላልችልም እያልኩ ግን ለዲሲዥን ትሪ it has already built in interpretability and explainability ደግሞ ቅድም ላይ መጀመሪያ ላይ ስንነሳ ከተርሞቹ እንድነሳ የፈለኩት ኤክስፕላኔቢሊቲ ግን ብላክ ቦክሶች የላቸውም። አሁን ለኒውራል ኔትወርክ እንደዚህ አይነት ነገር መስራት ይችላል በቀላሉ ማለት ነው። ሶ in order to understand this አሁን ለዚህኛው ግራዲየንት ቡስቲንግ ነው የሰራሁት። ለግራዲየንት ቡስቲንጉ ላይም እና ሻፕ እንጠቀማለን። እዚህ ጋር ደግሞ ፕሪምቹዋል እንትንም አለን፣ ፕሪምቹዋል ኢምፖርታንስ የሚባለው አለን፣ ፒዲፒ ይኖረናል። እዚህ ጋር ደግሞ እንዴት አፌክት እንዳደረገው ለማየት ከዛ በኋላ ደግሞ ሎካል ደግሞ ሻፕ እና ላይም ይኖሩናል። So we're gonna see እንዴት እነዚህ ነገሮች አፌክት እንደሚያደርጉት ግን we're not saying yeah okay እሺ ተመልሷል ጥያቄው መጀመሪያ or like I think ኤግዛምፕሉን እያየን ነው። እስቲ አሁን ለምሳሌ እዚህ ላይ እንዴት ነው የተረዳው?
እንትኑ ሀሳቡ ጥያቄ የሚያበዛት በደንብ አንደርስታንድ አድርጌ ለማድረግ ስለፈለኩኝ ነው።
በደንብ ምንም ደስ ብሎኛል ስለጠየቅ፣ ምክንያቱም ኢትስ ጉድ ቱ አንደርስታንድ። እኔም እየተማርኩ ስለሆነ የሚራብሬያቸው በጣም ደስ የሚለኝ እንደውም ጥያቄ ስጠይቁ እንደውም የስተርዴስ ሴሽን with the best session so far because there were a lot of questions and answers from both sides, so በጣም ደስ ይል ነበር። so እንደዛ እንዲሆን ነው እንፈልገው ነው። okay so so if it is clear, let's move. Thank you so much Abdul for the questions. Okay, for the rest, is it clear guys? Clear now? Are we on the same page? Can I see some confirmations? Okay, let's move on then. Let me just zoom in a bit in detail. So እነዚህኞቹ just some dependencies ናቸው። so train test split ይሄኛው ደግሞ የምጠቀመው ዳታ ሴት የብሬስት ካንሰር ስለሆነ እሱን ተጠቀም። ከዛ በኋላ from a scalar and linear model የሎጂስቲክ ሪግሬሽን ወሰድኩ። ከትሪ ደግሞ ትሪ ዲሲዥን ክላሲፋየር ወሰድኩ። ፕሎት ትሪ ደግሞ በኋላ ላይ ፕሎት ለማድረግ እንዲጠቅመኝ ወሰድኩት። ኤግዛምፕል ደግሞ ግራዲየንት ቡስቲንግ ክላሲፋየር ወሰድኩ። ከዛ ኢንስፔክሽን ደግሞ ፕሪሙቹዌሽን ኢምፖርታንስ እና ፒቲፒ ወይ ደግሞ ፓርሻል ዲፔንደንስ ዲስፕሌይ እነዚህ ኦልሬዲ ቢልት-ኢን ናቸው። ከዛ በኋላ ደግሞ ለሎካሎቹ ደግሞ ላይም እና ሻፕን ወሰድኩ። ለፕሎቲንግ ደግሞ ማትፕሎት ሊብ እና ሲቦርድ ወሰድኩ ማለት ነው። ሶ እዚህ ጋር ጀስት ሴቲንግ አፕ ዘ ቪዥዋላይዜሽን ነው። ከዛ የመጀመሪያ ስራዬ ኦፍ ኮርስ የሚሆነው ምንድነው ዳታውን አመጣው። የካንሰር ያለው የብሬስት ካንሰር ነው። ከዛ በኋላ ክላሲፋይ አደረኩትኝ። አይ ጀስት ቱክ ለትሬን እና ይሄኛው ኤክስ እና ዋይን አወጣው። ከዛ በኋላ ደግሞ ትሬን እና ቴስቱን 80% ለትሬን 20% ደግሞ ለቴስት አደረኩትኝ። ከዛ በኋላ we have 455 for the train and 114 for the test data set 30 ፊቸር አላቸው። 31ኛው ደግሞ is the prediction or the output. So የመጀመሪያው let's talk about the white model. So white model ላይ ሁለት ኤግዛምፕሎች እናያለን, which is the logistic regression እና ከዛ በኋላ ደግሞ የዲሲዥን ትሪን እናያለን። so እነዚህኞቹ ራሱ human can understand them, which is interpretability ነው ማለት ነው። so ቅድም ኤግዛምፕል እንትኑ እንዳትረሷቸው እነዚህን ሁለት ኤክስፕላኔሽኖች of the terms. That's why I think I have put them here. So the degree to which human can understand the cause of a decision by looking at the model itself. So ሞዴሉን አይተን እናውቃለን ማለት ነው። so እዚህ ጋር ትሬን አደረኩት ፊት አደረኩት። ከዛ በኋላ ኮኤፊሽንቶቹን አወጣው። ኮኤፊሽንትስ ዶት ሶርት ብላችሁ ማውጣት ትችላላችሁ። እዚህ ጋር ኮኤፊሽንቶቹን መጀመሪያ ስላወጣው ማለት ነው። ከዛ በኋላ ፕሎት አደረኳቸው። so you can see that feature coefficient from the logistic model ይሄ አሁን ከሞዴሉ ነው ከፕሬዲክሽኑ አይደለም ማለት ነው። just from the model we can see that እነዚህኞቹ አሁን ለምሳሌ ቴክስት ኤረር ይሄ ሚን ትንሽ ዙም አውት ላድርገው። so this is the mean or zero የምንለው ነው። so ከዜሮ or from this line ወደዚህ የሚወስዱት are ቤኒንጅ የሚባሉት ናቸው። ወደ ኔጌቲቭ ደግሞ የሚወስዱት ማሊኛንት I think የሚባሉት ናቸው ማለት ነው። so text error texture error more to the positive ነው የሚወስዱት እነዚህኞቹ በጣም ሌስ ኢፌክት ነው ያላቸው on the decision, but they do have effect። ከዛ በኋላ ደግሞ the highest effect ደግሞ ያለው worst concavity የሚባለው ፊቸር ነው። so እሱ ደግሞ more to the malignant ይወስዳል ማለት ነው። so ይሄኛውን አይተን ብቻ የሆነ ኬዝ ሲመጣ በጣም ትልቅ worst concavity ካለው we can identify that it's negatively ወይ ደግሞ ወደ ማሊግናንት እንደሚወስደው ማለት ነው። so እዚህ ጋር explanation አለ። this plot shows the model's learned logic feature with larger positive coefficient strongly push the prediction toward the range, and the feature with the largest negative to the malignant used a lot. So it's very easy to understand plus ደግሞ እዚሁ ፊት ለፊት ነው የምናገኘው ከሞዴሉ ማለት ነው። ሁለተኛው ደግሞ የዲሲዥን ትሪ ነው የሚያሰው የቅድሙ አለን ከዛ ዲሲዥን ሞዴል እንትናችንን አመጣን ከዛ በኋላ ፊት አደረግነው ከዛ በኋላ ፕሎት አደረግነው ፕሎት በምናደርገው ሰዓት we can see the decision tree if else ማለት ነው if ይሄኛውን የሚያሟላ ከሆነ ቤንጅ ነው ትሩ ከሆነ ወደዚህ መጣ ይችላል ከዛ በኋላ ደግሞ ይሄን የሚያሟላ ከሆነ it's ቤንጅ or ካልሆነ ደግሞ ፎርስ ከሆነ ወደዚህ ነው ይሄን የሚያሟላ ከሆነ if else ነው ማለት ነው so you can see እንዴት አሁን ለምሳሌ የሆነ ይሄኛውን የሚያሟላ ቤንጅ ካለን እንዴት አለን የሚለው we can identify it from these three so ከዚህ ተነስተን ፎልስ ነው ይሄኛው ወደዚህ መጣ ከዛ እዚህ ጋር ደግሞ ሲመጣ it's true ስለዚህ ወደዚህ መጣ ብለን we can identify it easily ማለት ነው በቀላሉ እንዴት ወደዛ እንደመጣ ማወቅ እንችላለን so these are very like easy to explain plus already built in ናቸው so these are called the white box models ከዛ ወደ ብላክ ቦክስ እንመጣ አንድ ኤግዛምፕል ነው ያለን of course for now we're going to look at the gradient boosting so here train እንትን አደረኩት ፊት አደረኩት በትሬኑ ላይ ከዛ በኋላ አጋጣሚ ሆኖ የሎጂስቲክ ሪግሬሽን ሞዴል አኩሬሲ በልጦታል ግን of course እዚህ ጋር ትዊክስ ስላላደረኩት ነው like the number of estimators and random state value tweak አድርገው of course it could go above it should go above the logistic regression accuracy and ያው so እንዴት እንደሚሰራ ግን ለማወቅ we have to do something so ለመጀመሪያው let's talk about the global post hoc explanation እንዴት እንደሚሰሩ so አንድ ጊዜ so sorry so እዚህ ጋር permutation importance የሚል already built in የሆነ ኢምፖርት ያደረግነው አለ ለሱ we just give it its inputs ከዛ በኋላ sorted index ደግሞ primary importance important domain እነዚህኞቹን ሶርት አድርገን ሰጠነው ከዛ ፕሎት አደረግነው so here the explanation could be so በጣም ትልቅ ቫልዩ ወይ ደግሞ ትልቅ ቼንጅ የሚያመጡት ወይ ደግሞ ትልቅ ኢምፖርታንስ ያላቸው permutation feature ኢምፖርታንስ ያላቸው ከዚህ ማን ናቸው worst concave point እና ደግሞ እዚህ ጋር worst perimeters እንደሆኑ ማየት እንችላለን like አንዳንዶቹ ጭራሽ ራሱ የሌላቸው አሉ አንዳንዱ of course አለው ነገር ግን worst area worst perimeters እነዚህኞቹ worst perimeter negatively ወይ ደግሞ ወደ ኔጋቲቭ የቅድሙን ማየት እንችላለን እና ማንን ወደዛ እንደሚወስደው ከዛ በኋላ ይሄኛው ደግሞ በጣም ትልቅ እንደውም ቼንጅ አለው ደግሞ worst concave point እንደሆነ we can see that so the plot shows how much the model accuracy drops when the features shuffled so እንዴት like የሆነ ስንቀያይራቸው ቫልዩዎቹ አሁን ለምሳሌ በጣም ስንቀይረው በጣም ኢፌክት ያላቸው እነማን ናቸው የሚለው we can see that ማለት ነው so እንዴት እንደቀነሰ እንዴት ደግሞ እንደቀየረው accuracy you can see so ይሄኛው accuracy ላይ ስለኛ decrease in the model's accuracy ነው እዚህ ጋር actually የጨመረም አለ so worst perimeter እንደውም ጨምሯል ግን እነዚህኞች በጣም ትልቅ ኔጋቲቭ ቫልዩ ያላቸው ናቸው ማለት ነው ደግሞ ኔጋቲቭሊ አፌክት ያደረጉት ወይ ደግሞ like ዲክሪዝ ያደረጉት ያሉት accuracyዎቹ ናቸው ማለት ነው worst concave point so እሱን መረዳት እንችላለን ማለት ነው and the PDP which is also very interesting when you take a look at how it works so ለዚህኛው how does the percentage change when we vary a single features value so for this one let's change the partial like the top gradient boosting line let's change I think you should partial dependency display from estimator sorry there is some noise sorry I think it's here okay yeah so here you can see that በዚህኛው ደግሞ በመጠቀም two ፊቸሮችን በመቀየር which are the worst concave point and the worst radius የሚባሉትን ትልልቅ ፊቸሮችን በመቀያየር we can see እንዴት አይነት ኢፌክት እንደሚኖራቸው you can see እንዴት ድሮፕ ሊያደርጉ ወርስ ኮንኬቭ ፖይንቶችን በምንቀይርበት ጊዜ ፓርሻል ዲፔንደንሲያቸው እንዴት እንደሚቀየር you can see ማለት ነው። so whereas concave point as value increases increase እያደረገ በሚሄድበት ጊዜ የሞዴል prediction probability drops like እንደምታዩት በጣም እየወረደ ነው የሚመጣው። እዚህ ጋር ግን እስከ ተወሰነ ይወርዳል። ከዛ በኋላ is going to be flat lined. Similarly, the radius of the tumor increases, the model becomes much more likely to predict malignant, which is lower probability of being gained. So እንደዚህ አይነት ነገሮች እነዚህ አሁን So is that clear, guys? መጀመሪያ let me confirm ከዛ ሁለቱ አይተን እንደርሳለን። I know I am taking a lot of time, but so is it clear, guys? እንዴት ዋይት ቦክስ ሞዴሎች እንደማን ናቸው? እንዴት ነው ማለት እንዴት ነው የምናያቸው? እንዴት ነው የምንረዳቸው? ኢንተርፕሬት እንደምናደርጋቸው ከዛ በኋላ ደግሞ ኤክስፕላኔቲቭ ላይ ደግሞ ስንመጣ ብላክ ቦክስ ሞዴሎችን ግሎባሊ እንዴት ነው አንደርስታንድ የምናደርጋቸው ነው። is it clear? ከዛ አሁን ወደ ሎካል የብላክ ቦክሶችን ሎካል ፖስት ሆክ ልናይ ስለሆነ I just wanted to know if there is understanding. እሺ የገባው እሺ confirm አልገባኝም ራሱ ጥሩ ነው። Someone or is it from my side? Okay, good. እሺ ዝምታ ወርቅ ነው በሚለው ይሁን። እሺ so let's talk about sharp. Sharpን በምናይበት ጊዜ sharp I just made some predictions ከዛ በኋላ እዚህ ጋር ማየት ትችላላችሁ። sorry. So explainer we have the sharp 3 explainer sharp values ይኖረናል። explainer dot values ቴስት ላይ ያደረገ ከዛ በኋላ ፕሎት አደረገ ከዛ በኋላ index 0 which is let's explain the first instance. So የመጀመሪያውን ቴስት ሪዛልት ወሰድ ቴስት ዴታ ሴት አለን። የእሱን ቴስት ዴታ ሴት ትሬንድ ማለት ፕሪዲክት ካደረገን በኋላ የእሱን ቫልዩ ነው ኤክስፕሌን ለማድረግ ነው በሻርፕ ማለት ነው። so ሞዴል ፕሬዲክሽን አለን። ከዛ በኋላ እዚህ ጋር I think it's better እስቲ በደንብ እንዲታየን so here የመጀመሪያው ሰመሪ ፕሎት ነው። ሰመሪ ፕሎቶቹ ማለት ምንድናቸው? የፊቸር ኢምፖርታንሶቹ ለዛ ስፔሲፊክ የመጀመሪያው የቴስት ዴታ ሴቱ የመጀመሪያ ሮ ቫልዩ እንዴት እንደመጣ ወይ ደግሞ እነዛ ላይ ያሉት ኢፌክቶች እነማን እንደሆኑ የሚያሳይ ነው። ሲምፕሊ ኤክስፕሌንድ ማለት ነው። so here the worst area በጣም ትልቅ እንትን ስለ እንደነበረ ያሳየናል። worst concave points አለ worst perimeters and so on and so on. ያ ትንሹ ደግሞ works I think compactness is the lowest ብለን መውሰድ እንችላለን። so we the mean sharp value and average impact on the model output magnitude ነው ማለት ነው። ከዛ በኋላ ደግሞ እዚህ ጋር ደግሞ like more እንትን ይኖረናል። ቅድም እንዳወራ ነው ብሉ ሬድ እና ብሉ ብለን ቅድም እንዳወራ ነው ማለት ነው። so እንዴት worst texture እንዴት እንዳገዘው or ደግሞ እንደጎዳው like positive እና negative ኢፌክቱን ማየት ይቻላል። so its impact on the model output sharp value ማየት እንደሆነ ማየት ይቻላል። here also we can see that እነማ ትልልቅ ቫልዩ እንደነበራቸው ለምንድነው ወደ ጎን የማያደርገው? ኦኬ worst texture ምን ያህል ኢምፓክት እንደነበረው so ወደዚህ ከሄደ slower ወደዚህ ከሄደ ደግሞ higher so በጣም higher ስለሆነ ወደ ማለጃት ሄዷል። okay so here explanation አለ. You can take a look at it and see or try to explain why things happen and እዚህ ላይ ያሉትን ስዕሎች በደንብ ያሳያል። so the bar chart የመጀመሪያው shows the sharp value magnitude confirming our global feature importance ቅድም ስናወራ እዚህ ጋር worst area እና worst concave points እንዴት ኢፌክት እንደነበራቸው we can see አይደል? እዚህኛው ላይ especially worst area በጣም ትልቅ feature importance እንደነበረው እዚህ ጋር ማየት ይቻላል። በጣም ትልቅ ዲፈረንስ እያመጣ የነበረው እሱ ነው። እዚህ ጋር ደግሞ በጣም worst concave pointsም እንደዛ ነበሩ። እሱን እዚህ ጋር ኮንፈርም አድርጎልናል። worst area እና worst concave points በጣም high feature importance እንዳላቸው ከዛ በኋላ ደግሞ ሁለተኛው ደግሞ the dot plot shows not only just importance but also direction of effect ወዴት ነው የሚያመሩት ሰው ወደ ማኔጃንት ነው የሚያመሩት ወይስ ደግሞ ወደ ዛኛው ነው የሚያመሩት የሚለውን ደግሞ ያሳየናል high words concrete point values are read pushing the prediction to the management so እዚህ ጋር words concrete points በጣም ቀይ ነው የሚያሳየው ወደዚህ ዳይሬክሽኑም አለ ከለሩም አለ ሰው ወደ ማኔጃንት ነው የሚያመራው ማለት ነው ሰው ሎወር ነው ወደዚህ ያለው so blue የሆኑት አሁን እነዚህኞቹን ላይክ በጣም ብሉ የሆኑት ኢትስ ቬሪ ሎ ኢምፓክት ያላቸው ከዛ ቀዮቹ ደግሞ ትንሽ ከሆነ ደግሞ ላይክ ሪሌስ ኤረር አሁን ለምሳሌ ወደ ማኔጃንት ነው ግን ኢታዘ ሎወር ኢፌክት የሚለውን እና ማየት ይችላላችሁ ማለት ነው and the last one force plot የምንለው ደግሞ it's explanation of one patient this value is average prediction red arrow worst radius and worst area are feature pushing the prediction towards the management and blue arrow አሮ ደግሞ ወደ ቤኒች እየመሩት የነበሩት ናቸው ሰው እነዚህኞቹ ወደዚህ ወደ ማኔጃንት እነዚህ ደግሞ ወደ አይቲንክ ተቀይሯል ቦታው ግን ያ ወርስት አሮ ወርስት ኤሪያ ወርስት ሬዲየስ እና ወርስት ኤሪያ አር ፑሽንግ ኢት ቱዋርድስ ሶ አይ ቲንክ ከለሩ ተለያይቶ ነው ኦር ያ በት ኢትስ ኔጌቲቭ ስለሆነ ወደዚህ የሚገፉት እነሱ ወደ ማኔጃንት እየገፉት ነው ወደዚህ ደግሞ እነዚህኞቹ አሉ እነዚህ በጣም ትንሽ ስለሆኑ አልገለጻቸውም እዚህ ጋር ግን እነሱ ደግሞ ወደ ቤኒች የሚገቡ ናቸው ማለት ነው and the last one lime ነው lime ደግሞ tabular lime explainer እናያለን ይሄኛው ነው በጣም ቀላል ነው which is just explanation ናቸው words concrete points ወደ ምን እንደሚወስደው ያ አሁንም ስቲል ያ አንዱን ነው የምናየው I think ኢንዴክሱ 0 ነው የምናየው ለሻፕ የሚወሰደው ከዛ እንዴት concrete points እና worst area ያላቸውን lime explanation for instance is that a question someone ነብዩ is that a question so እዚህ ጋርም ዘሴም ተመሳሳይ ዘሴም ስለወሰድን ተመሳሳይ የሆነ ሪዛልት ነው የምናየው so words concrete point እና worst area at the ones ወደ ኔጌቲቭ ወይ ደግሞ ወደ ማኔጃንት እየወሰዱት የነበሩት እነሱ ናቸው so እነዚህ ኤቪደንሶቻችን ናቸው ማለት ነው ምንድነው ይሄ ነገር እንደዚህ እንዲያደርግ ያደረገው የሚለውን መመለስ እንችላለን ይሄኛውን በማየት ማለት ነው ሲጋርም ይሄኛው ጋር ተመሳሳይ ነው ወርስት ኤሪያ እና ወርስ ኮንክሪት ፖይንትስ ጋር ያ ወርስ ኮንክሪት ፖይንት እና ወርስት ኤሪያ እነዚህን በማየት we can see that linear approximation ነው ይሄኛው more focused for a specific patient it identifies the worst concrete points was the strongest piece of evidence pushing the models to predict management it presents a very simple human-friendly list of the top contributing patterns for a single decision made so sharp ደግሞ more focused የሆነ result የሚያመጣው ማለት ነው so እንዴት ነው አሁንስ is it clear ሊታያችሁት explanation በደንብ ኤክስፕሌን ነው የምታደርጉት እርግጠኛ ነኝ ከአሁን በኋላ or not okay እሺ ጥያቄ ያለው ሰው አለ or is it clear in that case I will take it as a yes I think we can end the session here thank you guys for joining and have a great day I will be sharing it in the drive so make sure to check the drive folder okay just check the drive folder I will share it now okay bye